let's pull back the curtain on how the software that pretty much runs our entire world is actually built. It's not magic, even though it can feel like it. It's a really disciplined engineering process. And we're going to break down exactly how it works, step by step. Seriously, just think about that for a second. The app you use to order a pizza, or the one you use to listen to music. That all started as just a thought in someone's head. So how did it make that incredible journey from a simple concept to a fully working piece of software on your phone? Well, that's the path we're going to trace today. Okay, first things first. Before anyone even thinks about writing a single line of code, there has to be a plan. And I mean a really, really good plan. This first stage is all about nailing down exactly what we're going to build and, just as importantly, why. Now, to keep everything from just turning into total chaos, engineering teams follow what's called a software process model. The best way to think about it is like a recipe or a game plan. Some are super strict, step-by-step instructions. Others are much more flexible, like Scrum or XP, where you build things in little cycles. But either way, this model is the framework that holds the entire project together. This right here is one of the most important distinctions to understand. We're breaking down the rules for the software into two types. On one side, you have functional requirements. These are the whats. What should the app do? Simple. It needs a share photo button. But on the other side are the non-functional requirements. These are the how-wells. Okay, you have a share button, but it needs to share that photo in under 2 seconds. One is all about features, the other is about quality and the user experience. You need both. So you take all those whats and how-wells and you write them down in the super important document called the Software Requirements Specification, or SRS for short. This is the official blueprint. It's basically the contract that makes sure everyone, the client, the managers, the developers, is on the exact same page about what's getting built. Okay, so now we know what we're building. Now comes the really creative part, figuring out how we're going to build it. This is the design phase. It's a lot like an architect drafting a detailed technical blueprint before a single brick is laid. And a huge principle here is something called modularity. Look, you don't build a massive skyscraper all in one go, right? You build it floor by floor, room by room. Software is exactly the same. You take a huge, complicated system and you break it down into smaller, self-contained, independent pieces or modules. This makes the whole thing so much easier to build, to test, and to fix down the line. So what makes a good module? Well, that's where this idea of cohesion comes in. Think about a well-organized kitchen drawer, maybe the one for baking. You've got your measuring cups, your whisks, your spatulas. Everything for that one task is right there. That's high cohesion. In software, it means a module has one clear job, and all of its parts are laser-focused on doing that one job really well. Now, the flip side of cohesion is something called coupling. This is all about how tangled up your different modules are with each other. If you make a change to the user profile module and it suddenly breaks the photo sharing module, well, you've got tight coupling. And trust me, that is a recipe for disaster. It creates this ripple effect where one small change can cause bugs to pop up in totally unexpected places. So the whole point, the big takeaway here is this. The goal of any great software designer is to create modules with high cohesion and low coupling. You want these focused, independent components that do their job and don't step on each other's toes. That's the secret to an elegant, maintainable system. We've got a plan, we've got an elegant design, but now we have to get practical. We have to answer the million-dollar question, or sometimes the multi-million-dollar question. How long is this actually going to take, and what's it going to cost? And you can't just guess. One of the clever ways engineers measure the size of a project isn't by counting lines of code, because that can be super misleading. Instead, they often use something called function points. This is a way of measuring the software based on the functionality it delivers to the user. Things like inputs, outputs, searches. It's a much more consistent way to figure out how big and complex the job really is. So once you have a size estimate, like from function points, teams can then use models like COCOMO. I know, it's a funny acronym. It stands for Constructive Cost Model. And what it does is it uses data from thousands and thousands of past software projects to predict the effort, the cost, and the timeline for a new one. It helps turn estimation from a total guessing game into something much more like a science. All right, the code has been written, the features are built, but we're nowhere near done. Now, the software has to run what I like to call the quality gauntlet. This is the testing phase, and it's designed to find and crush every bug possible before an app ever sees the light of day. Now, this slide points out a really subtle but absolutely critical difference. On one hand, you have verification. That's asking, are we building the product right? Basically, does it match the blueprint we made in the SRS? But then there's validation, which asks a much deeper question. Are we building the right product? In other words, does this thing actually solve the user's problem in a way they like? You can build the wrong thing perfectly, so you have to pass both of these checks. And how do you actually find all those bugs? Well, there are two main approaches. White box testing is kind of like a mechanic popping the hood of a car and looking directly at the engine. The tester can see all the internal code. Then there's black box testing. This is more like a driver who just gets in the car and tests it on the road. They can't see the engine. They only know how to use the steering wheel, pedals, and buttons, just like a real user would. And testing happens in layers, building up from small to big. First up is unit testing, where you check each tiny little piece in isolation. Then comes integration testing, to make sure all those pieces work together without breaking each other. After that, the internal team does alpha testing. And finally, you release it to a select group of real users for beta testing to find those last few problems out in the real world. You know, great engineering isn't just about reacting to problems, it's about getting ahead of them. That's what risk management is all about. Teams sit down and identify everything that could possibly go wrong, and then they make a plan for risk mitigation, monitoring, and management. Basically, how are we going to reduce the risk? How will we watch for it? And what's our plan if it actually happens? It's about having a plan B before you even need one. And launch. The app is live. People are downloading it. But the journey is not over, not by a long shot. For most software, this is really just the beginning of a long life of maintenance, updates, and constant evolution. To manage all this ongoing change, especially when you have a big team working on the same code, version control is non-negotiable. It's absolutely essential. The best way to think of it is as a time machine for your code. It records every single change, who made it, and when. So if a new update suddenly breaks everything, you can instantly just go back in time to the last working version. It is the thing that prevents total chaos. So yeah, software lives on. It evolves through a formal process called change control to manage all the updates. It evolves through the reuse of old components to build new things faster. And sometimes, when the code gets really old and tangled, it goes through a complete overhaul, a renovation, if you will, called re-engineering to get it ready for the future. Which brings us to one last question to chew on. After seeing this entire structured process, from planning and design to estimation and testing, what do you think? Is building incredible software a disciplined science where you follow models and principles? Or is it a creative art that needs elegant design and intuitive problem solving? The truth, of course, is that it's this fascinating, beautiful mix of both.